Yes, sir, you can start.
Good afternoon again. This is the last lecture on the course of high pressure physics. And we will discuss some of the leftover topics on shock compression of solids. Please recall that much of the discussion that we had on shock compression of solids, so shock compression in general, was with the presumption that they are fluids, except towards the last lecture or so, we talked about solids when we discussed the issue of that beyond a certain threshold limit of compression, which we termed as Hugoniot elastic limit, there is a plastic flow in the material and it has a consequence in terms of the Rankine-Hugoniot curve. Let us see. Let me reiterate some of the things that we have discussed so far. One was how the information about the shock wave profile is uniquely connected to the Rankine-Hugoniot curve, or commonly called Hugoniot curve. Hugoniot can be obtained by measurements of shock and particle velocities. And we briefly discussed the methods to measure the shock velocity and the particle velocity. The reason I say these two measurements is because the jump conditions that we derived were 3 equations and 5 variables, and all it required that at least 2 be measured for unique specification of all measurable quantities under shock compression. However, the Hugoniot curve has no information about the structure or even the state of the solid under compression, and we will see in some of the issues that we'll discuss today. Even phase transition, except when they have a large volume change, they will not be observed. Specifically, the phase transitions which have small volume change, including melting, may not be identifiable if you look at the Hugoniot curve. It would not have any easily identifiable discontinuities or features. Now, much needed explicit information of the structure is obtainable by other techniques such as X-ray diffraction and XFs and so on. XFs to a limited extent because it gives essentially the coordination of a particular chosen atom. All the earlier measurements on the shock compression of solids basically aimed at studying the wave propagation. And the wave propagation per se doesn't require any specific information about the structure. So all conclusions about structure were indirect, more specifically by comparing the results or anomalies with the static pressure results. We also discussed that the microscopic strain is hydrostatic beyond Hugoniot elastic limit. And we discussed that in the context of lithium fluoride. We showed that in one direction, just 111, below the Hugoniot elastic limit, its compression, shock compression indicated the uniaxial strain features, while in 100 direction, beyond the Hugoniot elastic limit, it showed essentially isotropic compression, which means hydrostatic compression. And the reason for that we mentioned was because elastic plastic deformation. Now, generally, the Hugoniot elastic limit of the materials, specifically metals, is rather low, a few GPa, and hence most of the theoretical studies which deal with the shock compression of solids mostly presume that the microscopic strain is hydrostatic. But strong materials such as diamond and others would not be hydrostatic strain. So in those cases, one has to adopt specific ways to deduce theoretical results. Diamond specifically, we will show today that retains uniaxial compression up to almost a megabar under shock compression. There are issues which are related to the shock compression. We have not specifically talked about it. We'll briefly mention some of these today. These are the phase transitions which are observed to be very sluggish under static compression. Are those phase transitions also take place under shock compression? The reason we ask that question is if a phase transformation is very sluggish, it takes hours to days, then under shock compression, your immediate reaction would be that it would not take place because shock experiments are essentially at the upper end, at best, microsecond kind of experiments, but in many cases, a few nanoseconds kind of experiments. So if a phase transformation takes place under shock compression, it has to be very rapid. Slow or sluggish phase transition in principle should not take place. But what is amazing is, I'll show a couple of examples today. What's amazing is it indeed happens that most of the phase transformations which are observed under static compression also are observed under shock compression. Not all, but many do. And that actually raises another question. Are the mechanisms different in the two cases? Another question which we briefly discussed last time, I'll revisit it in a few minutes. Are the local structure of the molten state closely related to the high density phases? I'm saying, suppose you have a molten phase, let us say at about 20-25 GPa. And if you just cool it at that particular pressure, then the structure of the liquid, does it have a correlation with the structure that may just exist across the melting curve? And lastly, the question on how to obtain reasonable estimation of temperature under shock compression. We again discussed about that the temperature increases along the Rankine-Hugoniot curve. It also increases under isentropic, but it increases a lot under shock compression. So is there a way to find the temperature? Recall that the jump conditions had no measurables which could be easily identified with the temperature. So temperature stays in the background, but it certainly defines the thermodynamic condition of the material under shock compression. And it gets buried basically in the third jump condition, that was energy conservation. Commonly, temperature is estimated pyrometry or through Curie experiment comparison. We will again briefly see how there have been efforts recent years to measure the temperature in the shock compressed materials. So today, what I'm going to discuss quickly is a few recent investigations. Silicon, I briefly talked about in the last talk, and I will revisit this to make a few points. Then we will discuss about graphite and show that it transforms to a very unique form of diamond, which is called hexagonal diamond. Normal diamond is cubic diamond, so it transforms to hexagonal diamond, which has been perceived or theoretically predicted to be much harder than the cubic diamond. So then the noble metals, which otherwise look very monotonous under static compression, show some very unusual results under shock compression. we will you recall that we started the discussions about the shock compression by picking up an example of iron. We will revisit iron in the context of its implications to the geophysics and briefly touch upon the temperature issue under shock compression. So this example of silicon under shock compression I discussed in the last lecture in the last couple of projections. And the idea was to show that silicon, which undergoes a very large number of phase transformations under shock compression, under static compression, specifically the cubic phase transforms first to a tetragonal phase, which is called beta-tin phase. And then that transforms to the primitive hexagonal phase, and then to orthorhombic, and so on and so forth. What happens at a shock compression? Does it follow a sequence of phase transformations? So the first experiment which we did was to shock silicon to somewhere close to 25, 26 GPa to see whether there are any signatures of a phase transition. And what we noted is that beyond 26 GPa or 26 GPa or so, the cubic diamond phase abruptly transforms to simple hexagonal phase, or what is also called primitive hexagonal phase. You can see here some of the peaks have been identified as the subscript simple hexagonal. So the cubic diamond phase straight away going into the simple hexagonal phase. So generally, the reason I highlight this is mostly it is believed that simple hexagonal phase is related to the primitive hexagonal phase. Primitive hexagonal phase is related to the beta-tin phase, which is the tetragonal phase, through a displacer mechanism, that is through softening of a mode, and which makes it very rapid. And it's also been often assumed that from cubic to beta-tin phase transformation, because it's a first order, it has a very large volume change, is generally what we call as reconstructive, that it breaks the bonds and rebuilds it. It's because the cubic phase is a diamond structured, very clearly oriented directional bonds, while the beta-tin is a metallic phase. So it's a lot more, should I say, electron states are delocalized. So it doesn't have that directional bonds per se. So to see a transformation into which the cubic phase directly transforms to a simple hexagonal phase is in its own right very interesting result, because that shows a static. This result nobody could have obtained it direct from static experiments, because static experiments you cannot directly compress cubic phase into a higher phase without going through the intervening phase. But in the shock compression, straight away, if you go to the stability phase of another phase, the question arises, will it transform, will it not? And here is an interesting result, where the cubic phase transforms to the primitive hexagonal phase very rapid. And then, of course, beyond this, it melts. What was interesting was the experiment was so designed. If you recall, we talked about the shock reflections, that when this impactor came and made an impact on silicon, a shock was launched into this, which then went into the backing plate, which is lithium fluoride. Lithium fluoride impedance is more than this. So at this interface, another shock wave is reflected here, and that increases the pressure of silicon. Now, recall that we talked about multiple shocks lead to higher compression without raising the temperature. So suppose this phase of silicon to begin with was a molten phase, and if we reflected another shock back from the lithium fluoride, it will raise this phase to a higher stress and most likely will transform it to a, should I say, crystalline phase. That crystalline phase in any way related to what kind of density you expect at the temperature just before the reshock? The answer we found was yes, indeed. For example, if you had initial pressure here, which was about 30 GPa, and it had already, kind of molten, and then after rebound from here, a reshock, as I may call, from this interface, this went on to a higher pressure of close to about 36 GPa. And what we noted is that it had a mixture of hexagonal closed packed phase and the primitive hexagonal phase or simple hexagonal phase. With the density, obviously, if you look into the phase diagram, their density is being very, very close. And if you did this experiment at slightly still higher pressures, close to about 40 GPa, then you see only the hexagonal closed pack phase, which is a higher density phase of silicon. That means two things emerge out of this. The recrystallization of molten silicon to a high density hexagonal closed packed phase, again, very rapid. It happened in a few nanoseconds. So within a few nanoseconds, or at best tens of nanoseconds, liquid phase crystallizes into a structure, the density of which is very close to that of the liquid, implying therefore the liquid just across the melt boundary has in it the information about say the coordination number and so on, which should be comparable to the structure to which it transforms. I'll probably skip all details that I have already summarized and I've mentioned here. So let's go to the next one. The graphite. The graphite is a very interesting. I'll briefly discuss several results related to this. Graphite is known to be a layered material. It is a kind of layers of carbon sp2 bonded layers are stacked on top of each other to give rise to graphite. So it's called actually two-dimensional solid, if you will. It so happens that graphite, or we call it graphite, exists in various microstructures, should I say. I've shown here a couple of examples. Think of these as crystallites. Each of the crystallite has a unique c-axis. The c-axis is the direction normal to which these two-dimensional layers are stacked. So this is the c-axis. You can see in a normal graphite, there is a slight misorientation between the crystallites which constitute the graphite. Okay, almost all are pointing in one average c direction, which we call average c direction, but each crystallite has a slight variation with respect to that average c axis. The other extreme is as deposited paralytic graphite, or which is also commonly called paralytic graphite. In this case, the c-axis misorientation is rather large. You can see that this was only slight. On to another, here you can see very large difference between various crystallites. Okay, and this actually shows up also in terms of the average interplanar spacing of the graphite layers. So if it is very well ordered, it's about 3.35, and when it is highly disordered, it tends to get close to 3.44. So, and what's interesting is the microscopic this macroscopic features also show in the microscopic features. For example, if this is almost perfectly aligned, then each crystallite has atomic structure which is also just absolutely in order. We'll call it AB kind of a structure. You see, this is one layer and the red is another layer, perfectly in sync with each other. So this we call as hexagonal graphite, or perfectly crystalline phase, if you will. In this also there are two variants. I'll briefly mention those. But the other limit into which the disorder along the c-axis is rather large, you can see that epitaxy between two layers is rather very bad. There are relative or real a kind of disorder in the orientations. This limit is called turbostratic carbon. This is also graphite. This is also graphite. In this, there are two variants. One is called ZYP, into which this misorientation is only a fraction of a degree, in fact, about 0.5 or so degrees in the z-axis. Slightly, um, slightly worse than that is what is commonly called highly oriented paralytic graphite, ZYH, into which it is about 3 to 5 degrees, but still, few degrees, should I say. This one could be very bad, could be anywhere between 40 to 50 degrees z-axis misorientation. And this can be measured by careful experiments along which are measuring the orientation of the z-axis. So let me summarize some of these features. That the experiments which were done on graphite, they were a variety of kind. In fact, graphite has been a focus of high pressure studies right from almost 6 decades. The first shock experiments, which was done on graphite, was done with explosive shocking of graphite. And the recovered material was analyzed, and they found that it had cubic diamond left. So this led to a lot of excitement about this, because once the shock recovered material had diamond in it, that had implications. I'll just briefly mention this. Specifically, it has implications in terms of a meteor or a asteroid coming and making an impact with the planet. So if it has a graphite in it, then the kind of a diamond that you will see at those sites should have implications in terms of the stress level or the kind of an impact level that meteorite would have had with the planet. And lots of theories about, extinction of dinosaurs and things of that kind, which has been ascribed to these events, such cataclysmic events. Basically are deduced from this results. What is found is that when they analyzed the meteoritic sites, they found a variant of diamond, which was named as longstellite. Okay, so lots of observations of longstellite at various meteoritic sites were interpreted in terms of serious meteor impacts on the Earth. On the other side, the studies of the graphite under static compression has also invited large number of studies, specifically the paralytic as well as slight variation of hexagonal graphite called rhombohedral graphite has been studied more or less at times which are almost 6 decades back, such as this, into which it was found that these graphites transform into cubic diamond, which is most common form of the diamond known to man. But however, if you take a highly oriented hexagonal graphite, it was also shown to transform to hexagonal diamond. Theoretical investigations indicated higher activation barrier for hexagonal diamond than cubic diamond, that implying that to get hexagonal diamond, one had to go to much higher stressors, because the activation barrier was much larger. So the first principle calculation, the experiments also suggest not only that these two forms of diamond exist, they predicted a precursor or competing other super hard forms of carbon, which are sp3 bonded. Various claims have been made, having observed monoclinic, orthorhombic, body-centered tetragonal, and diamond, and so on. More experiments on under static compression established that relative abundance of cubic and hexagonal diamond also depends on the thermodynamic path to which it is subjected. There has also been another aspect to look into lost daylight, into which naturally occurring, naturally observed lost daylight from the meteoritic sites were analyzed with the help of TEM and other studies to conclude that what we are terming as hexagonal diamond and lost daylight is actually a cubic diamond with a large amount of disorder. The interpretation of the recovered samples, therefore, does not necessarily indicate the path of conversion between the static and dynamic pressure to same, because the path is very, very different. Recall that I said that relative abundance, for example, it depended on the path it is taken. Static pressure, you can typically, diamond is made by putting the material under static compression of several tens of GPa for days together at elevated temperatures. While I mentioned that the shock experiments will be over with in a matter of few microseconds. So the wave profile measurements and earlier plate impact experiments were done in somewhere in 90s. In fact, two celebrated experiments which attracted a lot of attention were, one was with a highly oriented graphite, the ZYB grade, which I mentioned that oriented with a misorientation of a fraction of a degree of 0.5 or less. So the experiment which was done with this showed somewhere around 20 GPa, and within 10 nanoseconds, this transformed to a high density phase. This created a lot of it was done at Lawrence Livermore, the group of Bill Dallas, and it appeared in 1991 in Nature. It created a lot of excitement. But the other experiment, into which the pyrolytic graphite was taken, it showed a lot of frustration in terms of transformation to the denser phase. So there were all kinds of speculation. Has it really transformed to a denser phase, or it has gone to highly disordered structure of carbon, including amorphous carbon. Okay. Now, these experiments very recently were revisited, and what was found was there was probably some error in the second experiment, because now the repetition of the experiments showed very similar results for highly oriented graphite as well as for pyrolytic graphite, which was probably having a misorientation of C-axis by several tens of degrees. The difference between the pyrolytic graphite and that was the transformation that still took place in nanoseconds. The required pressure much higher. I'll mention some of these results very shortly. One of the difficulty with earlier experiments, as I mentioned at the beginning, was there was no in situ information about what the structure is. So there are lots of papers which are written into what the denser phase is. Is it a cubic diamond? Is it a disordered hexagonal diamond, and so on and so forth. Okay. So recent experiments were carried out on highly oriented as well as highly disoriented graphite. Let me mention first, which was published in 2016, into which pyrolytic graphite, which is far less ordered graphite, was laser shocked, and the results, in situ XRD results, showed that above 55 GPa, graphite transforms to cubic diamond. Transforms to cubic CD is cubic diamond, transforms to cubic diamond around 55 GPa. But if you shocked it to much higher stresses of 170 GPa, then the structure was hexagonal diameter, not the cubic diameter. Okay. So this looked in a sense very contradictory to the continuum measurements of Bell Dallas and others to interpret as to what happened really. So these experiments were revisited. These were laser shock experiments which lasted for very short time. As recall that we had a discussion about this, that many of the laser shock material, the shocks are almost triangular in nature, which rapidly decay. So it can have some consequences of this. So these experiments were revisited with a gas gun, into which a lithium fluoride, a very thick lithium fluoride impactor was impacted on a graphite of several millimeters across. Recall this will be a few few micrometers at best. So this is several millimeters thick. So this comes and makes an impact on this, and the shock wave travels into graphite, and XRD, the X-ray diffraction is taken while the shock wave is passing this material. As a consequence, because the diffraction is taken when the shock wave is still in transit, you will see in the diffraction pattern a mixture of the transformed or the high pressure phase and the ambient phase. So this experiment was done in late 2016, and was published in 2017, and the results are here. So we did the experiments with a highly oriented paralytic graphite, which is ZYB or HOPG ZYH grade. And what is noted here is the spots, the sharp spots here, which are representative of highly crystalline, single crystalline nature of this. And when this material is shocked, so after about 100 nanoseconds or so, you can still see those sharp spots exist, and the material is not yet fully transformed. But at a later time, which is almost 290 nanoseconds, this has really transformed into a phase which the specific spots indexing indicates it is a hexagonal diamond phase. At a later time of 450 nanoseconds, when a part of the shock wave has actually been released, the diffraction pattern could still indicate that it exists in the hexagonal diamond phase. Incidentally, these numbering are essentially sequence numbering. Here are the indices for the hexagonal diamond phase. This is a repeat of the experiments at close to 300 nanoseconds. Incidentally, this big spot is basically because of the lithium fluoride single crystal, which was an impactor. You see that this is also single crystal. So a single crystal impacting this single crystal, and so this also gives large intensity low spots like this single crystal. So this can be interpreted in terms of very clearly identified orientation relations between the graphite and the hexagonal diamond. This is the kind of a bonding which is shown the hexagonal diamond. And what turned out, the 001, which is the C axis of the graphite, which is in this direction. Okay, that's the experiment were done with the impact was along the C axis. The impactor came and impacted along the C axis. So it is this axis of the graphite which was shocked. And when it was shocked, the kind of interplanar spacing was reduced and the bond formation took place between the layers, giving rise to the hexagonal diamond. What is very, very interesting in this result is not only that the lobby spots are hexagonal diamond, if you analyze it very carefully, this direction of the hexagonal diamond it has slightly smaller dimensions, 2.45 nanometer compared to this 2.248 nanometer, indicating that 100 direction of the hexagonal diamond was uniaxially compressed when it was formed. So it's a kind of a single crystal graphite transforming into a single crystal of hexagonal graphite. And this is very important because of in situ nature of this. See, the recovered samples earlier, which were either in the early shock experiments of De Carli and Jamieson, or of what was recovered in the meteoritic sites, the recovered actually means they were subjected to the rising edge of the shock wave, and then the steady part of the shock wave, and then the release wave. So it has whole history of the pressure time history to which graphite has been subjected, which has given rise to that. So if you will, I would say that's the post-mortem structure or post-mortem analysis of the structure of that remnant structure. It could have arisen either in compression or in steady state or on release and so on. But to see that actually this whole thing takes place within a few nanoseconds is very, very interesting. This is the question which I posed a few minutes back. For example, graphite to diamond, which is an extremely sluggish phase transformation requiring days, it transforms within matter of few tenths of nanoseconds. So obviously there is an alternative mechanism, and that is a theoretical challenge to the people who want to be about this. And to the best of our knowledge, so far nobody has done theoretical. I understand that some people have undertaken this, but so far no successful result has come into which the shock was launched along C-axis of the graphite to show how the hexagonal diamond really emerges out of this. So the high density is determined from XRD measurements and continuum measurements. Agree very well. I'll show briefly the PV curve which is resulting out of it. I already mentioned the wave profiles. Actually, it is not shown here. The wave profiles measured, recall, I mentioned that the VISAR or the wave profiles are being measured here, which is a lithium fluoride graphite window here. So from there, one can get profile measurements, continuum measurements. They actually match very well with some other earlier experimental results, specifically for oriented graphites. More importantly, that these results were in marked contrast with the earlier reported shock compression results on the pyrolytic graphite, which claimed that at 55 GPa, the transformation was to the cubic diameter. Ours, we did this experiments also at 50 GPa, and we showed that it is hexagonal diamond. And I think reconciliation of these two results is because they saw very limited diffraction data and they misinterpreted some of the features. For example, they had only one peak to interpret it as a cubic diamond, and two peaks of which one was very faint as hexagonal diamond. The other experiments are also carried out in the turbostatic carbon, which is a highly disoriented carbon, and compared with respect to highly oriented form. I'll quickly summarize the results. I've already said that when it is a highly oriented graphite, it transforms to the hexagonal diamond. But when it is a pyrolytic graphite, here, what we find is that it transforms to the cubic diamond instead. So this itself is also very unusual. That indicates that the initial microstructure of the graphite had very serious implications in terms of the structure graphite will take under shock compression. So highly disordered structure giving rise to cubic diamond, and highly ordered structure giving rise to the hexagonal diamond. These are the A-axis, C-axis plotted C by C naught as a function of pressure. What is noted is that for highly oriented graphite, which are ZYB or ZYH, which is up to this, where it transforms to the denser phase, the variation of C by C naught is the same for the same as that of paralytic graphite. So the paralytic graphite really transforms at much higher pressure. So that means the disorder in the paralytic graphite forces it much higher compression before it transforms, almost I think 30-35% more compression than what is required by the highly oriented form of the graphite. And the Hugoniot curve that one deduces out of this is before transformation, and this is a post-transformation, various results, even the continuum results, which did not have any idea of what the structure it will be or it is, pretty much agree with each other. So let me summarize these results quickly. That upon plate impact, in the under plate impact experiments to about 60 GPa, as deported paralytic graphite transforms to cubic diamond, which probably reconcile the results seen in earlier laser shock experiments. And the shock compression along C-axis to about 50 to 50 GPa, highly oriented form of the graphite transforms to the hexagonal diamond. And below the transformation, compression occurs mainly along C-axis. And highly oriented graphite has already achieved a comparable density to non-ordered, but while the ordered one transforms at much lower compression, the disordered one requires much higher, almost twice as much higher pressure. We move on to the next aspect of some of the results which are unique to the shock compression. Gold, considered the noblest metal, and because of its nature that it retains its characteristics irrespective of pressure and temperature, it has been widely used as a pressure marker in a variety of high pressure experiments. See, generally, I mentioned, showed specifically in other extreme example of graphite to diamond, the phase transition under shock and static compression generally have one-to-one compression, one-to-one correspondence. The question is it universal? Is it a universal fact? I mean, the question which I raised right in the beginning of this lecture, all the transformations are identical. Let's note that, in fact, an issue which was also discussed by Dr. Pandey in one of his talk, that gold stays in its initial structure, face-centered cubic structure, almost to a terapascal. It doesn't undergo any phase transformation up to the highest pressure measured so far, and also stays so up to the melting point. That's even if you increase the temperature, it doesn't undergo any structural change. And of course, theoreticians have ventured into trying to find out what could possibly be the structures which the gold can have at higher compression. And there are widely different results. People predicting a hexagonal close pack phase between 210 to 240 GPa, other group 350 to 410, and still another 420 to 710, depending on the computational method they use. So almost all those said the FCC phase should transform to hexagonal close pack phase at very, very high compression. There was also one observation from Germany, which claimed they did observe hexagonal diamond, but to the best of my knowledge, it has not been detected. It has not been observed by others. I also mentioned that the shock melting of gold was predicted again over a wide pressure range. Some at 120 GPa, others at 210 GPa, still others at 280 GPa. We carried out again experiments on gold thin foils, which are laser shock experiments. Math is shown here. This is the gold thin layer, and it has at the back the Kapton ablator and the laser, which is about 300 micron across, impinges on this, ablates this, and launches shock into this. And this is a lithium fluoride window, and which has a reflecting mirror here, which measures the velocity and therefore gives the information like this, particle velocity and so on. And the X-ray diffraction, X-ray which passes through this while the shock is in the sample of investigation, gives a diffraction pattern which is showed here. Okay. What we noticed very, very unusual feature was that somewhere between 150 and 175 GPa, FCC phase transforms not to the hexagonal phase, hexagonal perspective, instead to BCC phase at a pressure of 150 to 175 GPa. And that BCC phase starts melting at a still higher pressure of 220 GPa. So this was a very, very unusual result. It fell in, the continuum curve, the continuum Hugoniot was much in agreement with what was deduced by XRD. So these are the data points which you see, which are where the density is independently measured by the X-ray diffraction experiments, while this is the PV curve, which has been deduced by, should I say, continuum measurements into which the particle velocity and the shock velocity were measured. So the diffraction pattern has FCC structure up to about 150 GPa, and a mixture of FCC, BCC, at one, this particular example image has a mixture of FCC, BCC phase, and then at still higher pressure, there's only is that the gold melts. The gold melts somewhere close to 220 GPa. Unlike some people who claimed that it could melt, it may melt at 100 GPa. There are other issues in gold, and I'll come back to that. But before that, let me show what is the theoretical insights into what happens in the material when a shock is launched into this. So there has been shock simulations, these molecular dynamic simulations, and the results which came out are that if a face-centered cubic material such as gold is subjected under shock compression along 100 direction, which is a cubic isometric direction, then the results show there is a slippage along 4 available 111 planes by emission of shock fronts of Shockley partial dislocations. So dislocations getting generated at the shock front, which leave behind stacking faults. Stacking faults are faults in ordering of layers. Normally FCC is ABC, ABC, ABC packing. And when you say stacking fault, there's a jog. One of the layer gets missing. So let's say AB, AB, then it continues further. AB, one layer missing, then ABC, 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 and so on. So whenever there is a stacking fault, there is a jog which takes place in the stacking order. So these are the MD results which showed that at the shock front or the cubic axis, there is a generation of stacking faults. So simulations revealed that the slippage begins at the shock front in the form of bands of the stacking faults, and slippage also occurred on different types of 111 planes. And incidentally, this behavior is very similar to what has been conjectured to be what could be happening in the shock front in a perfect lattice. That was the work of Smith, which basically hypothesized this is to accommodate increased density at the shock front. And at the same time, the shears are leaving the shear stress. This is a image of what they observed in the MD simulations, Brad Holian and colleagues. And what are shown as these sharp lines are essentially the stacking faults. So material up to this has been shocked, and you can see a variety of crisscrossing things, which are essentially stacking faults. Each individual atom, if you blow it up, is shown here, much, much smaller. So the stacking order gets affected. So these are the results of Polian. I think the initial was 1998. So they are having subsequent experiments, subsequent MD simulations by other colleagues. And almost all showed that there should be a large abundance of stacking faults, but nobody knew how to observe this. The experiments were carried out on the recovered samples, which indeed showed large abundance of dislocations, stacking faults, and all kinds of faults. But then, as I mentioned, what you see in the post-mortem analysis doesn't necessarily have a bearing on what happens under shock compression. For example, the abundance of the dislocations in the recovered samples was found to be an order of magnitude less than what is expected if there is a donation of dislocations at the shock front. So we anyway, as I said, we did experiments on gold, and then we revisited this aspect. Can we interpret the diffraction pattern in a manner that it identifies the stacking faults? So I will not go into detail. The signatures of the stacking faults are very subtle. One has to be very careful about that. Incidentally, introduction of what stacking faults can do to the XRD is given in Warren's book, and those of you who are interested in can go through the details here. But more relevant work is a publication by Waltrop and colleagues in 2000, into which they showed if the abundance of stacking faults is large, then how will they affect the diffraction pattern? So one has to be, as I said, very, very careful to interpret the results. Because the shock experiments, incidentally, these are the various HKL peaks, and these are the indications of which peaks will shift how much, in which direction, and so on. Some will direct in the positive direction under the existence of stacking faults. Some will shift in the negative direction. So one has to be very careful. Remember that under compression, all peaks shift to the positive direction. So one has to be very careful about observing the nature of the shifts. So that analysis was done meticulously, spending several months of careful analysis on data, and which incidentally got published in PhysRevX, where I showed you geometry which was very similar to the previous experiments, where we observed FCC to BCC transformation. So in this case, the XRD image recorded when the shock is in transit in the gold sample, and this shows the existence of the shock wave in the sample. The X-ray diffraction pattern absolutely required me to put in percentage of stacking faults. And the reason is that these diffraction pattern cannot be analyzed by a normal software, which many of the static pattern people will do, write wide and so on and so forth. One had to write down the program into which all inputs go into what is absorption in particular direction, how much is input XRD, input X-ray profile, what is the nature of the structure it has, what is the kind of texture it may have, and so on and so forth. All these go into this, and the whole diffraction pattern is calculated. In this case, we had to put in the stacking faults. If we didn't put the stacking faults, for example, the calculated peak, specifically 200 peak, will be very different from this. So it will be somewhere here, calculation will be somewhere here, observed is somewhere there. So by careful analysis of the data, we could deduce and show that the gold had a very large abundance of the stacking faults, that close to about 140, 130, 150 GPa. It's a percentage of almost 16%, implying that every sixth layer is kind of is a stacking disorder. So the question arises, is FCC BCC transformation that we saw in gold has anything to do with the stacking faults. To establish or investigate this, more experiments are carried out specifically on silver. In silver, again, similar experiments, and the careful analysis of the data requires, again, a copious increase in the stacking faults, somewhere in 140 to 150 G or 160 GPa. But same experiments, similar experiments in platinum. Platinum also incidentally has FCC phase to begin with, up to as high as 380 GPa, did not show any stacking faults. Okay. So, like gold, silver also undergoes a transformation from FCC to BCC, but also has a large abundance of stacking faults, as shown here. In almost every sixth layer kind of stacking fault in silver, but in platinum, none. And what happens? And platinum also doesn't transform. So it seems very, very close relation between the abundance of the stacking faults and FCC to BCC transformation. I make that statement because that's something which doesn't happen under static pressure, because that we started by saying that the gold stays in the FCC phase up to a terapascal. It doesn't undergo any phase transformations. And hopefully, it also doesn't have much of the stacking faults. And so if it doesn't have a stacking fault, it doesn't seem to undergo a phase transformation. So apparently there is a correlation between the nature of the defects which get generated under the shock compression and the kind of the phase transformation a material can go undergo under shock compression. We recall that we started our discussion of the shock compression with an example of iron. We said that how the controversy between the work of Bridgman and that of shock compression iron actually combined these two topics and also established shock wave as a primary source of calibration. So these experiments of gold were actually very recently listed. It's no more at low pressure, but they're aimed at very, very high pressures, and the issues were very, very different. No more that initial phase transformation. This summarizes, for example, the kind of the phase diagram which was known. You see that it exists in iron exists in the BCC phase, and it's known to go into what is called as silent phase, which is hexagonal close back phase. At high temperature, it goes to FCC phase and so on. So some of these phases are known. Static high pressure work has also claimed observations of various other phases, such as double hexagonal close back phase, which is indicated here. Also claimed to have been observed over a very large range, or orthorhombic phase, and several other phases indicated by this cross. Okay, which is again a kind of an orthorhombic phase. So also there are a large number of studies which have tried to measure the melting curve of the iron, shown here with the brown line, or with the dotted line here, the shock deduced from shock compression. So there have been a very, very large amount of studies which have been carried out on this, but there are two questions which still required an answer. One, all static high pressure experiments are limited to less than 200 GPa. So the question was, what is the structure of iron beyond this? Second, this is the inner core boundary of Earth. What is the kind of the pressure and pressure? Okay, but what is the kind of a temperature which exists here? Can one get some idea with the help of the shock experiments? So with that as an intention, the experiments were carried out. I'll just quickly summarize the results that we got. There are incidentally very huge number of experiments which have been carried out here. For example, earlier experiments claimed that somewhere in between 200 and 243 GPa, the melting kind of has the iron melts over a very large pressure range of almost 40 GPa. There are others who claimed that it undergoes a structural phase transformation in this region. This also has been proposed that towards the core of the Earth, iron will be in the BCC structure because it's entropically stabilized, high temperature, high pressure. There are several numerous MD simulations which claim to support this. Other experiments established other various structures which I just a few minutes back indicated. So there's a large body of work which was done. So experiments, shock experiments established that HCP phase, the BCC phase transforms to the HCP phase. Okay? And then at higher compression, a diffuse scattering from the liquid emerges over a very small pressure range of 242 to 247, just about 5 GPa, in contrast to earlier where they claimed that it's almost 35 GPa. So over a very small pressure range, it helps. Now that had a very interesting implications in terms of constraints that one can have in terms of the temperature which will be there at the inner core boundary. I'll skip other details except saying that we go here first. These are some of the results which are shown here. So this is a kind of a melting temperature. This is the kind of estimated temperature and pressure for the liquid phase. This is one of the theoretical curve, and these are calculated along the Hugoniot. So we see amongst large body of the theoretical curve which have been calculated for as a melting curve as a function of stress, only one matches, and when this is extrapolated, it indicates a temperature at the inner core boundary to be close to, I think, 400 K, and this temperature here at close to 5400 K. The observed results are pretty much match with the laser shock with the continuum curve. So indicating that though there are a lot of changes which are happening in iron, the Hugoniot curve didn't show anything. It actually was very rich in changes that it undergoes. Before I conclude, I will just make a couple of comments about how the temperature is kind of estimated. It is done mostly by pyrometry, that the emitted spectrum which comes out of the shocked material is fitted to the gray body and then interpreted in terms of the possible temperature. Alternative mechanism has been to measure kind of shock compressed solid and see what happens to this. But before I do this, I mentioned that I will give an example into which establishes the uniaxial strain state in case of a material which is much harder. The Raman measurements and the shock compression, this is the kind of geometry which is used. I'll skip details for those of you who are interested. I can discuss in detail. Was carried out in diamond, single crystal diamond, and you should recall, single crystal diamond has this unique peak at 1333 wave numbers. But when you shock it along 110, that cubic symmetry is lost. So this peak splits into three. So you can track these three peaks as a function of stress or uniaxial strain and see that it does not converge into one. If it was hydrostatic compression, all of these will converge into one. So all the three peaks persist up to, in this case, 500 kilobars, but it has been now known that diamond continues to be elastically in the elastic state up to almost a megabar. Coming back to the shock temperature, you can use the Raman measurements to estimate the temperature. And the reason is the ratio of the intensity of the anti-Stokes lines and Stokes lines. these lines to this line intensities has a very well-defined form. This is a laser line plus the omega of the Raman active mode and minus Raman active mode raised to power 4 with the Boltzmann factor in this. So the ratios of this various modes can be fitted to evaluate the temperature. Here is an example, experiments carried on carbon tetrachloride, and these are the kind of measured temperatures and various other estimation. You can see it from pyrometry and so on. This is in case it was an isentropy, but the shock temperature much higher. So Raman measurements are one of the techniques which can be used to estimate the temperature. But then, because Raman is a very weak signal, if one requires to measure very high temperatures, which can happen under high compression, there's a lot of background scattering which will come from the infrared radiation. So signal to noise ratio becomes very poor, and its precision actually dwindles. So we evaluated the possibility that whether the Weller factor based reduction in the intensities of the XRD could be used for estimating the temperature. It looked very enticing. However, our detailed analysis, specifically on copper and gold and platinum, showed a fundamental problem which is unique to the shock compression, that a texture of the material, the foil, changes as it is shocked. So you can see here the experimental curve, which is a black curve, and these are theoretical estimates. You can see the much wide variation, indicating that XRD can't be used. But very recently, experiments which have been carried out on platinum using XS have been under similar approximations that we made for X-ray diffraction have been successful. And that's partly because XF doesn't have strong features which are dependent on the texture of the film that is used. The last example that I had taken was of germanium. I started with silicon by saying that you compressed to higher compression, silicon bypasses beta 10. And after that experiment, the questions are asked, does beta 10 exist under shock compression? So slightly different experiments, not on silicon, where the beta 10 would happen at very low pressures. Slightly different experiments were carried out in germanium, into which it was shown that indeed it transforms to beta 10 phase. These peaks are very, very close. One has to be very careful in analysis. The conclusions were that at about 15.7 GPa, germanium transforms to highly textured tetragonal phase, which is a beta 10 phase. At much higher pressures, it melts like silicon. And as the stress is released, the beta 10 phase very quickly, in matter of few nanoseconds, transforms back to untextured cubic phase. So the crystallization on release is very, very, very rapid, indicating that cubic to beta 10 phase change is reversible, and the recrystallization from the liquid phase occurs in a matter of nanoseconds. And so I guess I conclude here the high pressure course, and I hope you might have seen a variety of variation of behavior of materials when one goes from static pressures, static pressure low temperature, static pressure high temperature, static pressure under shear deformation, to shock compression, which rapidly compresses the material along with the temperature increase. There's a rich variety of phenomena which happen, and there are similarities, there are differences, and each material one has to analyze very carefully to deduce the fundamental changes that are happening in a material. Specifically, under the shock compression, we noted that the defects generated may be quantifiable and may have unique implications in terms of possible changes which might not happen under static compression. I guess we stop here, and I hope you people at least benefited in knowing certain aspects of the high pressure science. If you have questions on today's talk, I'll be very happy to answer. But if you don't have, it is fine. And if you have more questions later on all aspects of high pressure physics, please let HBNI know, and we will arrange to address some of the questions which you may raise. Thank you very much. Thanks a lot.
Hello.
Hello. So I'm done. In case there is some question, I'll take. Otherwise, we are done with the course.
Oh, I will check, sir.
Please.
We can wait for
Sure.
1 to.
Sure.
There are no questions, sir.
All right. Is it Rishabh or Anurag?
Yes, sir. Rishabh, sir.
Rishabh, thank you very much for